one direction on a freeway on a peak hour. Think about the morning commute, right? So in your morning commute, if you're going the same direction as everybody else is, you will be stuck perhaps on the standard morning traffic jam where everybody is trying to get to the office around 8 to 9 a.m. However, if you're going on the opposite side of the freeway, you will notice there are almost no cars on that part of the freeway. So you can see how the directional factor will impact. That might be about 80%. Similarly, for the afternoon portion of traffic, we have everybody trying to go back home around 5 to 7 p.m. So everybody's packing the freeway, to get back home. However, if you're going the opposite direction, then you will see that the freeway for your side is almost wide open. So that's what the directional factor tries to do, is so that you are cognizant that the direction of where cars are traveling impacts the design of the facility. And then we also have some other factors like the design speed, which is the maximum safe speed that you want to design the road for. And it's specified over a section of roadway. And the local, and whether you're designing for a local or a rural road. Now both AASHTO and HCM will have minimum design speeds. AASHTO will have minimum design speeds based on the geometry of a local and rural road. And the HCM will have minimum design speeds based on the level of service you want to achieve for those roads. And this facilitates the traffic flow in those specific types of roads and facilities. Note that the design features of the roadway will govern the design speed. Now, we're veering a little bit off topic on the PXM. But I need to mention this to you. When you're designing a roadway, it's the geometrics of the roadway that will control how fast you can travel on that roadway. It is not the regulatory signs that are on that roadway. So if you have a roadway, let's say, let me go to the extreme, 10 lanes wide, straight as an arrow, no hills, flat as it can be. It's almost as you can say as a raceway, right? And you have a posted speed of 20 miles per hour. Nobody's going to be going 20 miles per hour on that roadway. They're going to be going 80, 90 miles per hour, right? The opposite. If you have a winding road with narrow lanes that has many different pedestrian crossings, it has quite a bit of visual obstruction on the way, such as big trees and so forth. And you have a posted sign that says you can go 70 miles per hour on this wide, narrow road with different bends and turns. There's no way, even if you put your pedal to the metal, you're going to achieve 70 miles per hour on that road. You'll be lucky if you can get 20 miles per hour of moving on that road, right? So know that it is the geometrics of the road that control the design speed. It's not what you post on that road that will force people to travel at a specific speed. That is a key notion that you should be aware of. Now here we see the minimum design speeds for local and rural roads. And these are based on the design volumes, on the average daily traffic. This is based on the average daily traffic, not the average annual daily traffic. And see how transportation engineers like to divide their terrain into level, rolling, or mountainous terrain, right? So for flat terrain, you can see that Your speed will be about 50 miles per hour if you have large volumes. And if you have smaller volumes, you will have 30 miles per hour. So what does that mean, having higher volumes and less volumes? Well, that means two things. Either you have some kind of geometric constriction on your flow rate, right? That you don't have that many people going on that road. That's why your design speed is lower. Or you just have so much traffic on that road that you just can't go fast enough. Note the difference for rolling and mountainous. The steeper the grades, the lesser the design speed you want to put in because of your considerations for vertical curve design. Table 73.5 reviews these design speeds for local and rural roads, and you can see it on SERP. Now, you will not need to refer to this table to solve for a problem in the breadth portion of the exam. However, it's here just to help you refresh on the theory. And you can see how different road facilities vary based on their design volumes. And now we get to perhaps one of the main concepts in traffic flow rate as they apply for the breadth portion of the P exam, and that is the peak hour factor, which is also known as the peak hourly factor. So the peak hour factor is simply a division between the actual hourly volume and the peak rate of flow, all measured in vehicles per hour. Let me zoom in so you can see that, the subscript. They are all measured in vehicles per hour. So you may need to do some kind of conversion. If you have vehicles per lane, per hour, you just need to get it into vehicles per hour. The peak rate of flow within an hour is taken as 4 times the peak flow in 15 minutes. The peak hourly flow is always going to be less or equal than 1. The peak hourly flow is always going to be less or equal than 1. Which you can see that makes sense based on the bottom part of the equation. Now, how about we go through a problem to test the concept we have reviewed so far. So this will be our first problem on the geometrics lesson. So let's go through it. The number of vehicles was recorded for each 15-minute interval from 5 to 6. So let's just say from 5 p.m. to 6 p.m. our afternoon peak, right? And the time interval is shown on the left column of the table, and the volume in vehicles is shown on the right column of the table. You see the time interval is all in 15 minutes. So we have the total volume for that hour is 3,600 hours. I'm sorry, 3,600 vehicles. Now, what is the peak hour factor for the road? Is it 0.4, 0.6, 0.8, or 1? There are no units because the peak hour factor is just a ratio. So that should be giving us a clue, right? If you would like to solve this problem on your own using the concepts and equations that we have reviewed so far, I'll encourage you to go ahead and pause the video at this point before we get into the discussion of the solution. This problem is an example of one that may be encountered on the exam. You may encounter a problem that's very, very similar to this one on the exam. There are many parameters used to calculate the volume distribution on a given roadway. Now, exam problems may focus on these parameters for traffic flows. Now, if you'd like to look at an example of analyzing a larger data set than just the 4 15-minute measurements, please refer to example 73.1 in CERN, and you will see how a larger data set is analyzed. Now, of course, a larger data set will require a little bit more time. So that example problem does provide you some guidance on how to refresh on the theory, but keep in mind that the problems in the breadth portion of the exam are limited to be solved within 6 to 8 minutes. So let's go through the solution. Now we use equation 73.5 in CERN to calculate the peak hour factor for the 15-minute period. So the peak hour factor is going to be equal to the vehicles per hour divided by 4 times the 15-minute peak rate. So that comes out to be 0.8. So let me go back to the table to illustrate that. So the peak hour factor is going to be the division of our total flow rate within that hour of measurement, which is 3,600, or vehicles per hour, divided over 4 times our 15-minute peak. 4 times our 15-minute peak. So we need to review the data set and determine which is our 15-minute peak. That's 1100. So our peak hour factor is going to be our total volume in that hour divided by 4 times the peak 15 minutes. And that is going to be equal to 0.8. Now, on a larger data set, let's say we have let's say we're provided one more 15-minute measurement. And we are asked to determine the peak hour factor. So how do we determine the peak hour factor when we have more than a total of 1 hour of data? You may have 2 hours, 3 hours of data. But what you do first is you sum the first 4 consecutive 15-minute terms that yield the largest number will be your peak hour. So in our case, if we add 700 plus 900 plus 1100 plus 900, we get 3600. However, if we add 900, 1100, 900, and 1200, we get, and we dust off the old calculator. So we add 900 plus 1100 plus 900 plus 1200, we get 4100. 4100 is our hourly volume. So that means our hourly volume is shown right here. Now, if we were to determine the peak hour factor for hourly volume, we need to use the same equations. So volume in vehicles per hour for the entire hour, in our case, in our adjusted case, is 4100. And our peak value, oops, didn't mean to do that one. I wanted to highlight it. There we go. Then our peak 15-minute volume is 1200. So if we do our division of 4 times 1200, and this is also in an hourly volume, we get that our ratio is going to be equal to, let me dust off the good old calculator again. So we're going to get that our ratio is 0.85. Now that's if you have to evaluate a larger data set. You'll have to first find which of your 4 consecutive 15-minute terms yield your highest hourly volume. And then you need to, from those four, you need to pick the 15-minute segment that has the highest uh, density. And then you evaluate your total hourly density over 4 times your peak 15-minute density to get your peak hourly factor. Another way that NCS can test on this concept is that they give you two rows. Let me do another one so you can see. Let's say NCS gives you another row. The first row is volume of passenger cars. The next row is trucks. They give you, let's say, 20, 40, 60, and 40 again. And they tell you that the passenger car equivalent for trucks is 1.5 for this facility. So what do we do now? How do we solve for this problem? Well, we need to convert our trucks to passenger car equivalents. So we need to expand our chart and we need to multiply our trucks by 1.5. I'm just going to make my life easy here. I'm just going to say the factor is 2. So these are trucks, passenger car equivalent. Oops. And then we're going to have our total passenger car volume. Then we have 20 times 2 is going to equal to 40. 40 times 2 is going to equal to 80. 60 times 2 is going to equal to 120. 40 times 2 is going to equal to 80. And to get our total passenger car volume, we simply add them up. 700 plus 40 equals 740. 900 plus 80 equals 980. 1100 plus 60 equals, 1100 plus 120 equals 1220. And then 900 plus 80 equals 980. And our total volume is going to be, let me dust off my trusty calculator again. 740 plus 980 plus 980 plus 1220. It's going to be 3,920. Now we need to determine what our peak hour factor is. And that's going to be equal to my total hourly volume (3,920) over my 15 minutes of peak hour multiplied by 4, which is 1,220. So I dust off my trusty calculator, and that value would be 0.8. Now let me highlight 2 points here that might help you on a shortcut in the PXM. Note that trucks are being added in the same kind of general proportion as the volume in vehicles. That's why the addition of trucks might not necessarily impact the result of the peak hourly factor if you just evaluate the volume of vehicles. Now, I didn't do that on purpose. I just did it in a way to kind of like simplify the way I calculated for the problem. But if you note that the trucks are being added in the same proportion that the volume of the vehicles, you may skip all these other steps. However, if, for example, you see that the trucks are not added at the same proportion, one key thing is that you see 700 volume, 10 trucks, 900 volume, 40 trucks, 900 volume, 50 trucks. So they're not in the same proportion. That will impact your peak hour factor calculation. So you can see how NCS can test you many different ways for this kind of problem. So the more you practice them, the more accustomed you'll get to them. Keep in mind, once you have a solid footing on the theory and concepts for these kind of problems, you can tackle any kind of thing that NCS throws at you during the breadth portion of the exam. Let me clear the slate. Just as good housekeeping, right? Erase the board. So right now we're about the 1 hour mark, and we'll leave the continuation on our discussion of traffic flow rate for the next recording. So with that, I'll see you on the next recording.